Okay, so now let's look at number 2, microtransactions and in-game concurrency. So the first question here is a true or false, which asks us to mark all statements that are true. So let's look at the first statement, which says, in comparison to conflict serializability, view serializability is more efficient to check for complexity-wise. So remember that view serializability is weaker than conflict serializability, meaning like conflict serializability is a much broader check for serializability. So things that are conflict serializable are also view serializable, but things that are view serializable are not necessarily conflict serializable. So from that, you can imagine that view serializability takes, since it's a less broad check, like it's a more specific check, it takes more time to actually check for it. And in fact, view serializability is an NP-complete problem. So this statement is actually false. It's more complex to check for view serializability. Then the second statement is locks help enforce the atomicity part of the ACID properties. So the reason we have locks is to prevent different transactions from messing with each other, and that's actually the isolation property of ACID, so this is also not true. Then the next statement is the same graph can always be used for the conflict dependency graph and the weights for graph. So conflict dependency graphs and weights for graphs, the arrows in those graphs actually mean completely different things. So it wouldn't make sense to use the same graph for both of them. So that's also false. And then lastly, an advantage of strict 2PL over regular 2PL is the prevention of cascading aborts. So this is definitionally what strict 2PL is for. It prevents cascading aborts by forcing everything to abort at the same time. So in this case, this one is true. So this is the only statement that is true for this problem. Now let's look at part B on two-phase locking. So we're asked to analyze the following schedules and identify whether they follow two-phase locking. You may assume that all actions taken by the transactions are valid, and that the last action in the schedule for a transaction is the last action the transaction will take before it commits. So let's look at the first subpart of this, and we can take a look at this schedule and see if it follows two-phase locking. So what we notice is first, transaction 1 obtains an intent lock here on the database, and then transaction 2 obtains that same lock. Then transaction 1 obtains a read lock, an S lock on the table, on table 1 specifically, and then it releases that lock. Then transaction 2 obtains a lock, an X lock, a read-write lock on that same table. So this is all fine so far, right? These lock requests have not interfered with each other yet. Then we see that transaction 1 obtains an X lock on table 2. So remember that here in two-phase locking, we require all the locks. So once a lock is released, we require that the transaction obtain no more locks. So here, since transaction 1 had released a lock at this point, it cannot obtain any locks afterwards, right? So the fact that it obtains a lock here is a violation of two-phase locking. And so this schedule does not follow two-phase locking. Okay. Now let's look at the next part. So transaction 1 obtains an intent lock on the database, then it obtains an X lock on table 1 specifically. Transaction 2 obtains that same intent lock on the database. Then transaction 1 releases the lock that it had on table 1. Then transaction 2 obtains an X lock on table 2. So again, this all looks fine so far. They acquired intent locks on the entirety of the database, and then transaction 1 had an X lock on table 1, which it got rid of. And then now transaction 2 has an X lock on table 2. And then transaction 1 gets rid of its intent lock on the whole database. Transaction 2 gets rid of its locks at that point. Yes, in this case, the entirety of 2PL is followed because we can see that neither of the transactions obtain more locks after they release locks. So we're compliant with 2PL in this case. So in this case, we do follow 2PL. Then we look at subpart 3. So transaction 1, it looks like obtains, so it does everything in a cluster before transaction 2 in this schedule. So it obtains an intent lock to read the database, then obtains an actual read lock on table 1, then it releases that read lock on table 1, and then it releases the overall intent lock on the database. And transaction 2 essentially does the exact same thing, except it does it with X locks instead of S locks. And in this case, like none of the locks are interfering with each other, and we also see that after each transaction releases a lock, it doesn't go ahead and obtain new locks. So it's following the 2PL procedure. So in this case, we would say that it's compliant and it follows 2PL. Okay, now let's look at part C, which is on deadlocks. So we're asked to use the schedule of lock requests below to answer the following questions. Assume transactions hold onto any locks they obtain for the entire length of the schedule. If a transaction aborts, assume that it remains inactive for the remainder of the schedule. Also assume that priority is assigned by the time of first operation. So an earlier operation has higher priority. So let's look at the first subpart here. What transactions are deadlocked in the schedule? If there are multiple deadlocks, mark the transactions in the deadlock that will happen first. So let's do a waits for graph here to discover which transactions are deadlocked. So we have T1, T2, T3, and T4. So in this case, the first thing is T2 gets an X lock on B, then T1 gets an S lock on A. All good so far, nothing is waiting for anything. Then T3 gets an X lock on C, also all good. Now T3 wants a X lock on A. However, T1 already has an S lock on A, right? And S and X are not compatible, so T3 is going to have to wait for T1. So let's mark that in our waits for graph. So T3 is waiting for T1. Let me actually use a different color here just to make it more clear. T3 is waiting for T1. Then we see that T4 wants to read D. That's in this case fine. Nobody else has any locks on D, so no waiting there. Then T1 wants an S lock on B. However, T2 has an X lock on B, so those aren't compatible. So T1 is going to have to wait for T2 to release the lock. So T1 is waiting for T2. Then in step 7, we see that T2 wants an S lock on C. However, over here we see that T3 has an X lock on C. And so because those aren't compatible, T2 is going to be waiting for T3 in order to get that S lock on C. So we already see a cycle, right? So this is sort of the first deadlock. And we don't really need to keep going at this point because we were told to use the first deadlock. But let's just go ahead for the sake of it and go through the rest of them. So T3 has an X lock on D, or wants an X lock on D. However, note that T4 has an S lock on D, so those are not compatible. So T3 will be waiting on T4 there. And then over here in step 9, we see that T1 has an X lock, or wants an X lock on D. That's also the same situation where T4 already has an X lock, so T1 would be waiting for T4. And then we see in step 10 that T4 wants an S lock on C, right here. In this case, T3 still has that X lock, so T4 would be waiting on T3. So yeah. But we were just told to focus on that first deadlock, which, if you recall, looked like this. So that's the one that we will be focusing on. So in this case, we can see that T1, T2, and T3 are all in a deadlock with each other. Okay. So assuming no use of deadlock avoidance algorithms, do any of the transactions in this schedule complete? So in this case, right, T4 is not part of the deadlock, but if we so I'm going to undo this. If we sort of go back to the steps that we had filled in, if we go back to the steps that we had filled in here, we see, so let me quickly for a second. So yeah, so if we go back to this, we see that T4 is actually waiting on T3 because it needs that S lock on C, and T3 has the X lock on C. So over here, T4 wants the S lock on C, but T3 has the X lock on C. And so because T4 is stuck waiting for T3, but then T3 is stuck in a deadlock, T4 is not actually going to complete. So none of the transactions in this schedule complete. T1, T2, and T3 don't complete because they're in a deadlock, and then T4 doesn't complete because T4 is waiting on resource C, which T3 has. So then part 3, now assume that we use deadlock detection throughout the execution of this schedule. Which transaction should we abort to prevent further deadlocks for the rest of the schedule? So remember that so towards the end here, we see that T3 and T4 get in a deadlock with each other, because we can see T3 waits on T4 here, and T4 is waiting on T3 here. And so in order to avoid that deadlock, we need to abort T3. If we abort T3, that will prevent them from eventually getting into that deadlock. Okay, so now part 4. Now assume that we use wait die deadlock avoidance, which transactions are aborted. So remember for wait die, what happens is if transaction 2 needs a resource that transaction 1 has, let's say transaction 2 is older than transaction 1, then it's going to wait on transaction 1. If transaction 2 is younger than transaction 1, it's just going to die. So with that in mind, let's take another look at the schedule. So here, the first few locks go through without a hitch. Transaction 2 gets an X lock on B, transaction 1 gets an S lock on A, then transaction 3 gets an X lock on C, right? No conflicts so far. None of them are requesting locks on resources that are already taken, right? So all these 3 locks are given. The first sort of conflict happens when T3 requests an X lock on A, but T1 already has an S lock on A. However, notice that T3 is actually a younger transaction than T1 because its first operation occurs after T1's first operation, right? T3's first operation is at time step 3, but T1's first operation is at time step 2. So based on wait die, T3 is actually going to die, right? And it's going to abort here because it's a newer transaction. So T3 aborts. Now we're on step 5. So T4 asks for an S lock on D. Nobody has a lock on D at this point, so that's fine. Then we see T1 asks for an S lock on B. However, T2 already has an X lock on B. So T1 at this point right, those locks aren't compatible. So there's a conflict here. But however, T1 is a younger transaction than T2 because T2's first operation was at time step 1, whereas T1's first operation was at time step 2. So because T1 is younger than T2, T1 is going to die. Now we're on time step 7. So T2 requests an S lock on C. That's going to go through fine because the only 2 locks right now are an X lock on B and an S lock on D. So T2 is going to get that S lock on C, no issues. And then T4 wants an S lock on C, which doesn't conflict with T2's S lock on C, right? They can hold those simultaneously, so there's no more issues here. So to answer this question, T1 and T3 both are aborted under a wait die scheme. Now let's look at part 5. So now we're using wound wait deadlock avoidance instead of wait die. So in this case, if transaction 2 needs a resource that transaction 1 has, and transaction 2 is an older transaction, it will kill transaction 1. If transaction 2 is a younger transaction than transaction 1, then it will just wait on transaction 1. So now we take a look at which transactions are aborted. So let me quickly erase this. So again, the first few locks are given without issue. Right, so we have transaction 2 has an X lock on B, transaction 1 has an S lock on A, transaction 3 has an X lock on C. Then transaction 3 asks for an X lock on A. Because transaction 3 is younger than transaction 1, it's going to wait on transaction 1, right? So right now T3 is waiting on T1. Nothing gets aborted yet. Then we see that transaction 4 requires an S lock on D. Nobody else has a lock on D, so no issue there. Then transaction 1 asks for an S lock on B. Transaction 1 is younger than transaction 2, so it's going to wait on transaction 2. Then transaction 2 asks for an S lock on C. However, transaction 3 already has an X lock on C. But because transaction 2 is older than transaction 3, it's going to kill or wound transaction 3. So transaction 3 is aborted. That means we skip over timestamp 8 because transaction 3 got aborted. So the next request we see is transaction 1 asking for an X lock on D. However, transaction 4 already has an S lock on D. But because transaction 1 is an older transaction than transaction 4, we're going to abort transaction 4. And at that point, everything is done. So in this case, transaction 3 and transaction 4 were both aborted.